Hi guys, this is Mrs. Hayes with video notes 4.1, Intro to Exponential Functions. So you're looking at some triangles. We have figure 1 and 2 and 3 and 4. And it says in exercise 1, we're going to use these figures to answer the following questions about the number of black triangles. So you're going to make a table. Well, I don't know about 0 yet. Let's start with figure number 1 and look at the 1. I count 3 black triangles. You need to see them. They got red dots on them now. In figure 2, I could count them 1, 2, 3, 4, 5, 6, 7, 8, 9. In figure 3, it seems like there's a lot to count, so I'm going to get smart. I'm looking at what happened here. This original black triangle became this one, which broke into 3. Each of these broke into 3 triangles, right? So for each of these, there were 3 more. I'm going to say that means there would be 27 if I counted them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Yep, 27. So each of these black triangles is now going to be 3 more. So I'm thinking we multiply by 3 again, and we get 81. And then multiply by 3 again, 243. Multiply by 3 again, 729 black triangles. So what would happen if I reversed it and said, no, figure 0? Let's just count like that's a counter. Figure 0. It doesn't make sense to say it, but figure 0. I would imagine that means I started with 1 black triangle. I was trying to make that black. 1 black triangle. Because he then would split into those 3. So I'm thinking this would be 1. And if you look at the pattern, multiplying by 3, reversing direction, divide by 3, I would have a 3 divided by 3. Yep, 1 makes sense. How do you know this pattern is not linear? Well, if it was linear, there'd be a constant rate of change. So if you look at the jump of 6 and then the jump of 18, you can see that there's not, as these are going by 1, a constant rate of change. So the rate of change is not constant. Also, you're not adding the same number each time. Could have said that. We're not adding the same number each time. The same number each time. Then it says, write this situation as a function. Well, I'm going to call the figure number x and the number of black triangles f of x. So we have f of x could be found by starting at 1 and repeatedly multiplying by 3. 3 times 3 times 3 times 3 and so on reminds me of like 3 to the 4th. So what the number is that you're raising it to would be the x value. So think about that. If you were at figure 3, for example, figure 3, you would have 1 triangle that you started with, and you had to multiply by 3 to get to figure 3, 1, 2, 3 times. So your exponent would be a 3. That's what you're replacing the x with. And then you would end up with 3 to the 3rd power, which is 27. Use this function to determine how many black triangles. So here's our function. Use this function. F of x equals 1 times 3 to the x. In figure 20, that would be an f of 20. 1 times 3 to the 20th. I'm going to go to my calculator, and I'm going to type in 1 times 3 to the, is a little caret over here, 20. I get that huge number, 3, 4, 8, 6, 7, 8, 3, 4, 8, 6, 7, 8. Let me go back to my calculator, 4401. 4401. Would it make sense to find the value of x equals 4.5? I'm going to say no, because x is a counter, and we don't count in decimals. We count x equals 1, 2, 3, and so on. It's counting the figures. Find the equation of each function below. So we are starting with, I like to look at 1, 5. We'll think about the 0 in a minute. Technically, our y-intercept is that, so we are starting at 0, 2.5. And we are repeatedly multiplying by 2. If you look at the pattern, each time this goes up by 1, this goes up multiplying by 2. So I'm going to say my function would be start at 2.5 and repeatedly multiply by 2, and x counts how many of those 2's that you need. So 2 to the x. In the next one, we're starting with our initial value. I'm going to call that the initial value now because I know you've heard that before. So our function would be, what are we multiplying by? Ooh, that's not nice. If you want to figure out what you're multiplying by, you could always divide. So I'm going to go to my calculator and take 7.5 and divide it by 5 to see what it was I was multiplying by. So on my calculator, 7.5 divided by 5, control divide, 7.5 on top, put a 5 on the bottom. Let's see. 5 on the bottom. Control enter gives me a decimal, 1.5. Or if I didn't do control enter, it would have been 3/2. So 1.5 is what I'm repeatedly multiplying by. I could test another one too. If I did 9 divided by 7.5, divide by the previous number, and you'll keep getting 1.5. So starting from 2.5, this is a page number, by the way. Starting from 2.5, I multiplied by 1.5, and x counts how many of them I need to multiply by. On the next page, consider the function f of x equals 2 to the x. But notice I said 2 to the x. Complete the table of values below. So it looks like they started here with a -1. If you do 2 to the -1, that means 1 over 2 to the first power. A negative exponent is a power in the denominator. You learned this when you did scientific notation. So 2 to the -1 would just be 1/2. Let's do 0, 2 to the 0. If you look at it on your calculator, 2 to the 0 would give you 2 to the 0, a 1. Anything to the 0 power gives you a 1. 2 to the first is 2. 2 to the second is 2 times 2, which is 4. 2 to the third, 2 times 2 times another 2 is 8. 2 to the fourth, 16. Multiplying by 2 each time. If you reverse the pattern and divide by 2, that's where the 1/2 comes from. Divide by another 2, 1/4. Another 2, 1/8. Another 2, 1/16. So dividing by 2 if you're going in that direction. You'll see it if you do 2 to the -2 on your calculator. That's 1 over 2 squared. It's 1/4. 2 to the -3, 1 over 2 cubed is 1/8. 2 to the -4, 1 over 2 to the 4th is 1/16. Do negative inputs give negative outputs? No. For example, 2 to the -3 meant 1 over 2 cubed. It makes a fraction. Consider the exponential function 4 times 2 to the x. 4 times 2 to the x. What's the starting value? Well, if you look, it's this 4 in the front, just like we saw on the last table, on the previous page, I should say. Also, you could find that by doing f of 0, and you would see 4 times 2 to the 0. 2 to the 0 gives me a 1, and 4 times 1 is 4. What's the multiplier? Well, that would be this guy, the base, 2, because it means you're going to start at 4 and you're going to repeatedly multiply by 2 as you move through your table. So here we go. Let's take a look at this. It says verify using technology. We're doing 4 times 2 to the x. So 2 to the 0, 4 times 2 to the 0. That's 4 times 1. It'll give me a 4. That's my starting value. If I put a 1 in, 4 times 2 to the 1. 4 times 2 is 8. multiplied by 2. If I put a 2 in, 2 to the 2, 4 times 4, 16, multiplied by 2. Keep that going. Reverse it by dividing by 2. Oh, crap. This would be a 2. Divide that by 2, divide that by 2, divide that by 2. And we could check this out on my calculator. 4 times 2 to the x looks like this. Let's figure out which page I did this one on. 4 times 2 to the x is right here. Control T. There's my table for the 1, the 8, the 16. Look up the table and you'll see the negatives. They did the negatives as decimals, but I did them as fractions. Graph the function. So if you're going to graph this, you would start at 0, 4. The scale is going by 2s, 4, 6, 8, 10. So here's 0, 4. And then I would go to 1, 8, 2, 16, 12, 14, 16, 3, 32, and 4 would be off the table. And then backwards, negative 1 is 2, and negative 2 is 1. That'll be here, and you keep getting closer and closer, but never really, these fractions are going to get smaller, but never really approach, or never really hit 0, because you'll always have a positive 1 on the top. So the graph is going to go like this. Closer and closer and closer and never hit. So f of 2, if I want to know what it is at 2, I go from 2 up, or I look right here, should be 16. This says state the domain. The domain is negative infinity to infinity, because the graph goes as far left and all the way to the right as it keeps going up. Find the value of x when f of x is 2 or when y is 2. I'm going to draw a line here at y equals 2. I could also look at where y equals 2, but I'm going to see that that happens at negative 1. So x equals negative 1. State the range, that's the low to high values. So my lowest value is this line at 0 that it never touches. Never touches means use a parenthesis, and it shoots up to infinity. So 0 to infinity. What's the equation of the asymptote? That's this dotted line it never touches. It's the x-axis, and that's always where y equals 0. So the equation is y equals 0. What's the y-intercept? If you look at your table, that's 0, 4. And if you look right here, it's 0, 4. How does that relate to the equation? When x equals 0, y will equal 4. You could actually plug that in and see. What was my equation? 4 times 2 to the x. 4 times 2 to the x. 4 times 2 to the 0. Anything to the 0 power is 1. And that's a 4. Average rate of change. Oh, we have some background music, some drilling going on. 0 to 2. Put in my x's, get out to my y's. 0 to 2, 0 was 4, and 2 was 16. 0, 4, 2, 16. This change from here to here is an increase of 12 when this increases by 2. 12 over 2 is a rate of 6. That rate is not the same. As you go up on the graph, it gets steeper, and it has a steeper rate of change. It's not constantly 6, just from 0 to 2. Hope you enjoyed the video. Thank you for joining me.